Hello, good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our Citizen Science Q&A. Today we are going to talk about the Unistellar Citizen Science program, highlighting some brief results we got over the past months and answering to your questions. My name is Franck Marchis. I'm a Chief Scientific Officer at Unistellar, and I'm also the Director of Citizen Science at the SETI Institute. And with me, we have Lauren Sgro. Hello, Lauren.
Hi. Good
Lauren,
morning, good afternoon, good evening from wherever you're watching from.
are you stealing my lines already? My line already? Okay. So
Oh, I'm
Lauren,
sorry.
Lauren
It's
is
my
on the
favorite thing.
Exoplanet Leads and Outreach Manager at the SETI Institute. She works mostly for the Unistellar Citizen Science program. So she's the right person to talk about everything related to stars and supernovae and things like that. Okay. So Lauren, since we're talking about
Yes.
star and supernovae, why don't we just start with Tycho?
Yeah, absolutely. So I think that this is our second citizen science Q&A. So if we didn't get to your questions last time, we'll answer them today. And feel free to, of course, ask any additional questions that you may have in the comments. But first, we did want to start talking about some of the recent results and things that the Unistellar network is up to. And one of them is, of course, observing T Corona Borealis, which is expected to go nova within the next about year. And so we've been watching it, hoping that we're going to catch it. And as of July, so last month, can't believe it's already August. As of last month, we've been observing this star and potential nova for a year now. And
Mm-hmm.
have tons of observations, have a really long light curve from all of our citizen astronomers, but we haven't seen it explode yet. Franck, do you want to talk about some
Yeah.
of the recent scares that we've had?
So this is a program that was established by Tom. Hello, Tom. I don't know if he's watching us now. Maybe it's too early, or he's in the train.
Probably not.
But so Tom's implemented a new system into our pipeline. So I remind people: we observe, you send the data to our server, and we have a pipeline that analyzes automatically the data and deliver as an outcome a report that you receive on Slack if you are a citizen scientist at Unistellar. And on the top of that, we have now some kind of analyzer live that basically look at the data extracted, especially specifically in the case of TCO here, and check if there is an excess of brightness in this new image that you have collected. And if that's the case, Tom implemented a system that alert us. So when I say alert us, it's basically alert the citizen scientist via Slack, send text message to me and to other people, send an email as well, etc. So if one of us on this continent or on this planet is awake, he or she will receive this alert. Um, so I don't know when was that. 2 weeks ago, basically,
Yeah.
we were working in Arizona in Sedona on another project called Laser SETI, and we were after a long day of work. We
A
came
very
back
long day.
a very long day. We can finally come back in our hotel, and I was like, "Yeah, finally relaxing." Go to bed, and I hear my phone, and I take my phone, and here I see Tico may be erupted. So it was what,
Yes.
midnight or something like that.
It
And
was
Tom,
midnight. Yeah.
yeah, Tom was in Chicago, so it was probably 2 a.m. for him. So I called Tom, I woke him up, and he looked at the data, and that was a false alert. A false alert
Yes.
because nothing is perfect. Of course, there can be something can happen. There can be some cloud. There can be some perturbation into the system of airplane passing by, whatever. And that
Yeah.
was typically one of the false alerts. So we're learning, and we are making this system more robust. And the
Hmm.
goal is to have this implemented as well for comets in the future. So we will know when the comet is basically fragmenting or erupting or have some kind of sudden activity.
Exactly. And then if we are able to get these alerts or notification that the nova or has erupted or the comet has the comet has outburst, then that means that we can gather some of the most important data on that object. So that's why this is so important to be able to catch those things immediately. And I just saw that somebody asked how far TCRB, which is the abbreviation for T Corona Borealis, is. I believe it's about 2,500 light years away. So not super far, astronomically speaking, but it's still far enough to be interesting.
And
it would
far
be
enough not to be dangerous to us.
Exactly. But still, it would be visible to the naked eye potentially if it was to erupt. So that would be really exciting.
Okay, I see a lot of people watching us from Sweden, from Nepal, from Minnesota, from Moscow. I don't know if it's Moscow, Russia, or Moscow, United States, but I will say Moscow. From Quebec, another one from Minnesota, from England. So thank you. We are discussing the citizen science program at Unistellar and highlighting some of the results at the moment. And we will take some time to answer to your questions as well. Let's talk about the second thing, which is about asteroids. I like this part.
Absolutely.
Special love for asteroids. So,
of course you do.
Part of our program at Unistellar is to observe asteroids, especially the one which fly by our planet. So those are near Earth asteroids. But we also have a program that we started recently to characterize large main belt asteroid for which we don't have a shape model. It's weird, but there is still a lot of large asteroid, and I'm talking about typically 40 kilometers and above, for which we don't have enough data, so we don't have an estimate of the shape of this body. So how do we estimate the shape? It's a bit. I'm gonna display that. I don't know if we explained that last time, but we're gonna re-explain. So let's assume that this is an asteroid. Okay. So when you observe the asteroid from Earth, you don't see the asteroid itself. You see only the light reflected by the sun on the surface of the asteroid. So what you see from Earth is what we call the projected surface. So the projected surface changes as the asteroid is spinning, because an asteroid is irregular in shape and is also spin on itself, typically in 10 hours, but there is some which orbit spin in way longer than that. So when you see an asteroid and you take multiple data, you will see a variation of the light, of the brightness, and that's called a light curve. So this is due to the rotation of the asteroid, and if you observe it for a long period of time, at different because of the inclination of the orbit, you will see the asteroid tilted like that or tilted like this and spinning as well on its axis. Over the years, people have developed algorithm. We call that inversion algorithm. Mikko Kaisenlainen from Finland was the first one who did that, in fact, in the year 2000. And now we're working with Josef Dürer and Josef Anush from Charles University. And we are using a more complex model called ADAM. And this allows us to, from the light curve of multiple observers, combining them, using also archive data to get the shape of an asteroid. So we did that for two main belt asteroids called Impella and Isolda. And of course, I just realized I don't have my notes in front of me, so I don't really know what we found, but we have a shape model. Can I share my screen on this thing? I think I can.
I just shared mine.
Okay. Well,
this is Impella.
This is Impella. So it's an asteroid which has an irregular shape. And what's important here is that we get the spin period, also the pole orientation. So we know how the pole is with respect to the ecliptic, and we get as well an estimate of the shape. It's an estimate because those kind of model will not allow to see concavity. Okay, so I can talk about this in more details in the future. So we have generated those files, those 3D shape models. We have printed some of them, like this one. If you want them, we can send them. They're also on Slack, on our Slack Citizen Science. We can print you on mini asteroid if you participated to this campaign. I don't know how many observations you have. Do you have the data for this, Lauren?
I don't know how many people we had observed, but we did observe this particular asteroid for about 2 months, and that data was able to break the degeneracy and land on one shape model that we know to be true.
And one pole orientation. That's really truly important for that. Okay, so that's the kind of study we do. So like using your Unistellar telescope and observing an asteroid, you help refining the shape, the pole orientation, and the spin period of an asteroid. Okay,
pretty cool.
Let's go back to stars. We're gonna alternate, so this way everybody will be happy. So let's talk about exoplanets.
Oh, exoplanets, yeah. That's my favorite thing. So recently, the Unistellar network was worked with some other people in order to essentially track down a star that was originally discovered by TESS, and the group that we worked with expected that there was an exoplanet transit, and we helped them out by observing at a lot of different times when they expected an exoplanet to actually do its transit or pass in front of its star. And there were quite a few days that this could have happened. So the Unistellar network observed as much as they could. We didn't actually catch the transit, but the observers who did take part were able to submit their data, and then that helped the group as a whole to actually find out when the least likely periods were that the transit would happen, and then eventually catch the transit itself. And so that actually resulted in a Nature publication that was just published a few weeks ago. And this particular star, or this particular exoplanet, is one of only 3 that is eccentric enough that we can label it a warm Jupiter that is actually going to become a hot Jupiter. So I'm getting a little tongue-tied. But essentially, we have a lot of hot Jupiters that we know about. They're really easy to observe and catch and study. Even though our Jupiter-like exoplanets in our solar system, our gas giants, are cold, there's a lot of hot Jupiters out there in the universe, and we don't really know where these come from. We do know that there are gas giants that are a little farther from their star. We call these warm Jupiters as opposed to the hot Jupiters, which are really close, but we don't fully understand the trajectory from becoming a warm Jupiter to a hot Jupiter. And this particular exoplanet that the Unistellar network helped to discover is actually one of only 3 that is a warm Jupiter that we know will become a hot Jupiter. So that's really going to help our understanding of how planetary systems as a whole form, and potentially contribute to our understanding of our own planetary system.
So you don't have an image of this exoplanet?
I mean, we don't have
That's
an actual image of it. We do have, here, I can show you something. We do have an actual orbit, and I'll show that in just a minute. We have a simulation of the orbit.
You have a simulation where we basically, from the data, you derive the orbit, basically.
Correct. Correct.
I mean, exoplanet and stars are great, but there is not much to show in most of the cases.
Yeah, that is very true.
I'm a mean person early in the morning. But
okay.
yeah, it's going to be only simulations. But hey, it's a very cool result, and it was published in Nature, which is one of the most difficult, most selective journal in science with Science Journal. While you're looking for the picture, let me say hi to people joining us from Dallas, Texas, Ottawa, Qatar, Oromia in Ethiopia, Guyana. Welcome. We're talking about the citizen science at Unistellar. Did you find this picture?
It's going to take me a second. I wasn't prepared to show this particular
while you're looking
one.
for this picture, let me talk about something different. So we have new tools that we implemented recently in the citizen science program at Unistellar. And I think I can show my screen. So I may be able, while you're doing this.
You should be able to.
to show my screen and show some of this new tool that was developed by our citizen science team here. Share the screen. Okay. So this is our citizen science page. And this tool here, let me give you the larger version. This is, of course, when I do a demo, it's not going to work. Hey, it does work. All right. So this tool shows who has been observing over the past 24 hours. And this is generated every time you log in, you do a reload, it will basically display again, generate a new movie. So what you can see is that at 21 UTC, we have people observing in Europe. At 4 a.m., they're starting on the East Coast. At 7 a.m., they started on the West Coast. Then we go to Australia. We have no observer in Japan yesterday. That's weird. But maybe the weather was bad in Japan. That's the reason. So this is kind of a good way for people to visualize where the data is coming from. So far, you can see we have observation from 3 continents. I don't know how many of them. I will estimate something like 40 or 50 of observations based on the number of telescopes popping up. And the color of the telescopes also is an indication of the science which has been done for our telescopes. So as you can see, a lot of people are doing cosmic cataclysm because they're all trying to detect the beginning of T-Core B, which is great because that's exactly what we want. We want to maximize the number of observers so we see the beginning of this eruption. So you can visit this on our website. The link is up there. So it's science.unistellar.com. And then the new tool we implemented, which is more technical, but I do personally like it because I watch it every morning, is the Unistellar, the statue of the data processing. Remember, I mentioned that we receive the data and they come from on our pipeline, and this pipeline processed automatically the data. So now you can see what data is being processed by our server at the moment. So, for instance, for Comet, there's an observation of the Comet A3. We're going to talk about this one taken by this telescope, 52A. That's the first 3 digits of the telescope from Warners Bay in Australia, and this is being processed. We have observation of an occultation of 2006 BR 100, which was observed by two observers. This is the idea of the telescopes, and one was successful in terms of processing, and one has a failure. So this is a good way for us to alert our citizens, our scientists, to investigate and see what happened with these observations. So if you have taken data and you uploaded the data, you will see your location on the map, and you will also be able to see the status of your observation by looking at this website and also on Slack. Okay, that's all for the. Oh, maybe I can just show that. This is a cool way to visualize asteroids. It's a tool that you can get for free on Google Chrome, and you upload our OBJ file, so you can basically see the shape of the asteroid that we talked about previously. That's all. That's all for me. All right, I need to make sure I don't leave the studio and I stop the about to. Okay, go ahead.
I'll show this orbit really quickly, and then we'll probably. I wanted to talk a little bit about Comet A3. But let's go ahead and maybe get to some questions first.
Okay.
Just so that we have time. Let's see. And okay, there we go. So you can kind of see just in this particular screenshot of the simulation how eccentric the orbit around this exoplanet's orbit is around its host star, and how close that it comes because of the eccentricity of its orbit. And that is part of why this is called a hot Jupiter. So there's a visualization. It's really nice, but with exoplanets, it's a little bit hard when we're doing transits, because there's not a whole lot to see except for the light curve from the from the star's light changing as the exoplanet passes in front of it.
Okay, so the system is not seen like this from Earth. That's why I wanted you to point it out.
Yes, that is very true.
This
When
is
we
top
have
view of
a
the system, because now what
yes,
we see the age on view. That's why we see it.
correct.
Right.
Exactly. So when an exoplanet transits, we have to be looking at it from a certain point of view such that the planet and the star are in the same line of sight from our viewpoint, so that when the exoplanet passes in front of its star, we can actually see that dip in the light curve, which Franck was explaining about earlier in the case of asteroids. But it's a similar concept. It's just how the light is changing over time.
Okay, let's take a question. First question from Bob.
Yeah, let's do it. Let's see. Bob Donahue had asked this question, I think last time, and we didn't get to it. So he asked, when will a variable star monitoring program be introduced? So I can speak really quickly to that. We do work with AAVSO, the American Association of Variable Star Observers, and we don't have a variable star program like we do for the other programs where we're providing predictions and providing targets all of the time, many targets, on a given day. But we do have a monthly target from AAVSO that we observe through our Cosmic Cataclysms program. So we are, in a way, starting up that variable star monitoring program that you're talking about, and that may extend further in the future as we have more targets. But for now, it's one a month, and we get observations based off of what AAVSO feels like they need and what is interesting.
Yeah, we are doing it as a kind of a test for the moment, to be very direct. And as more data being taken, we will discuss with AAVSO to have a real program integrated into the app. We have a second question from Bob. You want to take this? I'll take this one.
Yeah.
So this is about solar systems. I'm going to talk about this. So when will the asteroid occultation program be running again? Well, it's already running. We basically stopped it for, I would say, a month and a half or 2 months for multiple reasons. First, we have to go back to the whiteboard and rethink the way we will be doing this. Let me give you a brief overview. So when we started Unistellar, that was the first program, the first scientific program we implemented, because it was relatively easy. The occultation consists in simply seeing a star disappearing or reappearing. So that's something we knew we could do with our telescope. We work with NASA, Lucy Mission, and AFA on implementing more interesting scientifically speaking program, searching for occultation of Trojan asteroid, for instance. So we did that on the first 2 years. And then on the third year, we decided to really test the limit of the system. So we implemented a lot of, we basically calculated occultations for a lot of asteroids. So if you are going to our prediction page at the time, you will always have an occultation from your house observable at any night. There was a lot of processing, a lot of calculation, but the problem we had is that by adding all the asteroids possible, like larger than 3 kilometers, that was our limit at the time, we had a lot of negative occultation, because the smaller is an asteroid, the least its orbit is known. So the likeliness of you catching up an occultation is very small. Typically, for a 3-4 kilometer asteroid, it's 1 out of 100 chance of getting an occultation. So a lot of people get a bit annoyed by that, because there was not a lot of positive occultation. But for us, it was extremely useful because it allowed us to collect a large number of data and truly understand the limit of our system and train, for instance, the AI algorithm that we've been using now to detect an occultation. So now this has been done, we pause and we rediscuss this program with Joseph Anush from the Charles University, who joined us, and we decided to focus on large asteroid and larger than 40 kilometers typically, and maximizing then the number of chords and potential positive occultations, with the idea of refining the shape of an asteroid. So it's back, but it's different. It's back in a way that you have less occultation, typically 1 per week for your location, will be more likely to get a positive one if you are on the band of centrality that we display on our website. Does that make sense? Apparently, everybody said it
I
makes
think
sense.
so.
Great.
And
All
we
right.
also actually had another person ask about occultations because they were expressing some frustration just about traveling to the path of an occultation and trying to get that positive result and not seeing that occur for them. So maybe you could speak to if some occultations are more likely to be caught than others, and how a citizen astronomer may
Yeah.
determine that when they're looking
So
at things to observe.
once again, when an asteroid has a large size, it's very likely that the prediction is accurate. And if you don't know the size of an asteroid, you should know that the brightest one was the first to be discovered. So typically, any asteroid which has a number less than 4,000, 7,000, a small number, will be a large asteroid. So will be likely to be you will be very likely to see the occultation if you're on the path of centrality. We will improve that. That's something that Joseph is thinking about with his team. One of the idea will be to rank, and in fact, we have a semi-ranking that you may see on our website, but it's not yet fully accurate. So there will be some occultation which will be highlighted in orange, and those will be very likely to be positive if you're on the path of the occultation. So we're working on this. It's going to come pretty soon. In fact, there is already a test run, and we hope to have that done in the next 2 months.
Great. We have a few more. Let's see. So we'll go back to exoplanets because I'm selfish. So Tateki Goto asked how many exoplanets have been observed with the network. So I was just looking at this morning, and since we've begun the program, there have been observation opportunities available for about 660 different exoplanets. As far as goes how many of those that we've observed as a network in the past few years, that number should be around 600. So that actually surprised me when I was looking at that data. That's a lot of different exoplanets that we've gathered data on. And it all comes down to our citizen astronomers and how dedicated they are, which is really lovely. And I think Tateki actually asked another question. Let's see.
Can I add something about this?
Yeah.
It's something I want to remind people that, yes, we have a lot of interesting results. I mean, we mentioned this Nature paper and so on, but the reason we have interesting results is because there is a lot of observations. The only way you can get interesting results in astronomy in observational astronomy is by observing a lot of targets. Okay.
Yes.
The one scientific paper in Nature is because you probably have observed 600 planets that were not that interesting, and there is one who finally is going to be interested. So that's the thing that people need to understand, that the more they observe, the more we collect data, the more scientific result we will get in the future. We understand more the system, better the system, I would say, and we also cherry pick the ones which are extremely interesting for publications.
Exactly. And oftentimes that requires data across multiple groups and multiple, different types of observers. That's why science is really meant to be such an inclusive thing. I mean, if you wanted to read that, go ahead.
And sometimes we don't see the gain of the benefit of observing an exoplanet right away. So we store it into the AVSO database, for instance, and then it's later on that someone go back to this data and can find some interesting motion, for instance, of the orbit, variation of the orbit. So that it's accumulative, basically. When you take an observation of an exoplanet, it could end up by a Nature paper in a few months, or it could end up in a Nature paper in 6 years.
Exactly. And I just wanted to tell everybody watching, if you were interested in that Nature paper, that was led by a group at NORA Lab that we were a part of. So that would be Gupta et al. 2024, led by Arvind Gupta. So if you wanted to go ahead and read that and see how our data actually contributed to that, that would be the place to look. So let's see. There's one more about exoplanets here from Tateki. So the naming rules for various names of exoplanets, it kind of depends on how well characterized the host star of that exoplanet is. For stars that are well characterized, we basically slap on a lowercase letter to the end of the star name. So, for instance, a star, say 51 Pegasi, then that would have its first exoplanet that was discovered as B. So the first exoplanet around that star would be 51 Pegasi B. And then subsequent exoplanets that are discovered would have lowercase letters appended to that name that are in the order of discovery. So there could be 51 Pegasi B, C, et cetera, just to give you an example. And then for stars that are less characterized, that exoplanet will typically be named after the observatory by which it was discovered. You'll see that a lot in the ones that we observe with the Unistellar network. So for example, Kepler 167e, et cetera, et cetera. You'll also sometimes see exoplanets that orbit one star in a binary system. And for those cases, it would be, for instance, I don't actually know if this is a real planet, Kepler 16 capital A B. So that would tell you that that first discovered exoplanet orbits around the primary star in that star system. So that the naming system for exoplanets is pretty well characterized in that way. I hope that answers your question.
And I have one thing to add is that pretty names for exoplanets are basically decided by the International Astronomical Union, which is an entity of astronomers, and they meet every 4 years. And there is one happening right now, in fact, in South Africa. And generally, what the IU have been doing is some kind of opening competition or suggestion from the world to name exoplanets. And I think we have official name for exoplanet for 370-ish of them now at the moment. So meaning they have a real name, and the star has also a real name, not a number, not a B, a real name. And that's pretty cool, I think, because we will have to name more of those exoplanets in the future. Okay,
and
we
some of them
almost
have
at
some
the
real
end of
nasty
our
names.
time.
Yes.
Let's talk about Comet A3 because I think it's important we discuss this. You want to show?
Yeah, absolutely. So I'll show you the light curve, which is very interesting. Oh, here we go.
So while you're
So
doing
do you
this,
want to?
I'm explaining what we do with comets. So
remember,
comets are bodies coming from the outer part of the solar system. When they come close to the sun, they're getting warmer, they're getting activity. So for us, human, we will see that they are becoming brighter, and they start having a coma, then a tail, etc. So Comet 2023 A3 to Chinchan Atlas, that we're going to call Comet A3, starting from now on, has been observed from January to July, and we're still observing it. And this is once again the light curve. So this is time versus brightness. Okay, the smaller is the number, the magnitude, the brighter it is. So the comet is coming closer to the sun. So what we expected a behavior like the white line you can see here. Maybe you can see it with your pointer on the top. I cannot. So you have the screen. So there is a white line here, and that was basically the prediction of the brightness, the evolution of the brightness of the comet from the first data we got. Well, something is happening to this comet. It's getting fainter. It started in mid-April, typically. You can see there is a dip, and it's basically drifting away from this theoretical brightness that we see. What is happening? It's not very clear. Ariel is working on that, and she has been doing some modeling of this dip in the brightening, and it may be due to some kind of phase angle effect. So that's the yellow line, if I remember, where basically there is some dust in the comet produced by the comet, and this dust, because of the size, has an impact on the brightness of the comet. And that's why we see this dip. The reason it's important is because this comet had a predicted magnitude based on the white line, which was zero magnitude in October 2024, October 2024, meaning that it will be as bright as Vega. However, now we have this phase angle effect. The brightness may be significantly different. Ariel has a prediction of, for this orange, the color is unclear to me, but for the yellowish, you can show the big one, the overview.
Mm-hmm.
You can see that the peak brightness will be minus 2.3. You need to show the second slide too, so we see that, Lauren. You have the second figure?
Yeah.
Okay. You don't.
It's just a little harder to see, but let me pull that up.
So the second figure show basically the predicted brightness based on this new modeling. So it's a very cool news because it means that the comet may be brighter than expected because of this phase angle effect if it lasts. This phase angle effect may not last, unfortunately, because it's also related to the type of material ejected by the comet. I mean, maybe the comet will change of type of activity. There will be less dusty and more gaseous. We don't know. But in any case, what is important here is that because of the monitoring of this comet with our instrument, we have, I don't know, like I can count, but there is more than 50 people here who have been observing this comet from April 2023 to now. We can see this effect, and we can now get a better prediction. So this clearly shows the complexity of comet activity and how difficult it is to predict the brightness in the future. So we will see. Exactly. What do you think, Laura, is going to happen? It's going to be 0? It's going to be -2?
I don't know. I would really like for it to be -2. That would be fantastic, and it would be so bright. But like Franck was saying, this just shows that there's so many things happening with this comet. It could be, outgassing, and its volatiles are getting depleted, so maybe it's not going to be so bright. Could be breaking up. The phase angle effect, all of these different things that even with all of these models, it's hard to tell, which makes it really exciting. So even if it's, a magnitude of -2 or, it's dimmer than that, I'm still really excited because whatever it is, we're going to hopefully be able to find out what's been going on with this comet that's showing all of these different behaviors that we weren't expecting.
Yeah, and if you look at the figure in the last point in July 2024 is one of the last observations taken, you can see that now we're entering into kind of exponential growth in brightness. So the comet is going to now change significantly. It's going to be very different from one night to another one. So we're going to clearly confirm if this modeling is correct or if it's is going toward more like the white line here. So if you did not do it yet, take some time to observe Comet 2023 A3. It's easy.
It's very pretty.
20 minutes, plus it's a pretty target to observe with your telescope. Okay.
I agree.
Shall we wrap up? We have a few things, maybe with some minor announcements you want to make.
Sure. First of all, if we didn't get to your questions this time, I think there was one or two more that we could answer on our next Citizen Science Q&A. So please continue to show up, and we'll go through our results and finish answering your questions. A couple of other things. We have a Exoplanet campaign that will be coming up this month. I'm spoiling a little bit, but it will be on our website soon. So watch out, especially if you are an observer from Europe and you want to participate in our most recent Exoplanet campaigns. Be watching out on our Unite website on science.unistellaroptics.com.
Say the name. Say the name of the
Unite.
program. Oh, Unite. Okay. All right.
Well, it's a part of Unite. So Unite is Unistellar Network. Investigating past exoplanets.
She's being mysterious.
So we have a new program that's part of Unite that's called Up Tempo. and we are basically looking for exoplanets that TESS missed. TESS saw indications of these exoplanets, but for whatever reason, didn't pass through all of the checks to be an exoplanet candidate or a target of interest. So we're going after those and trying to see if we can confirm those exoplanets. And our first observation was a couple of weeks ago, and that was visible from the US and South America and Canada as well. And it seems like we may have caught something really interesting. So our next attempt at that will be in a few weeks. So watch out on the website and on the Slack for that next September campaign.
We need to wrap up because I have a meeting and YouTube.
Okay.
So
Tanager, do you want to talk about Tanager?
Yeah, Tanager. So we started, I don't know if you have seen our website, we started the satellite program. And we have one first target, it's going to be Tanager. So Tanager is a satellite that will be launched by a SpaceX Falcon 9 rocket, probably August 15-ish, okay? And Tanager is a carbon dioxide observer satellite manufactured by Planet Labs, a company in San Francisco. And they connected with us because they would like us to follow Tanager as it goes towards its orbit and see its brightness when you reach this final orbit, to understand basically how this new technology they have been using to lower the brightening of those satellites works. So we are going to have a campaign specifically on Tanager just after its launch, all the way until it reaches its final orbit. It will be on our prediction webpage. And I hope you will contribute. This is kind of a cool new way to do scientific observation with unistellar telescopes and making something useful for humanity, because observing satellites will be very important in the future. And to go back to the Comet A3, the perihelion is September 27. So that means it's gonna get brighter and brighter between now and September 27, and the perigee is October 12. I saw that George Simar is asking questions about it. Yes, you can see the evolution of this comet-like curve over time. We try to post it every week, and I will make sure that Ariel does that the next 4 weeks, because we want people to see how the new observation is fitting or not the prediction that we made for this comet. And that's all for me. Where are you doing this summer, Lauren?
What am I doing this summer?
Yeah, for the rest of the summer. Are you going
for
somewhere?
Fun? I'm doing my job. I'm gonna do great at my job. Thanks, boss. I'm gonna go to Mexico. It'll be fun. I wish I could take a telescope, but I can't.
I think you should take a telescope if you go to Mexico.
No, I'm not doing that. You cannot make me do that. I've already no. I'm not working. I'm not working.
I'm going to Armenia tomorrow to a star party organized over there, and then I'm going to the Observatoire de Haute-Provence in France for a star party and for a talk. And I hope to see some of you, Unistellar user in France, at this talk and hopefully at the star party. So thank you very much.
Thanks, everybody. Thanks for tuning in. We'll see you next time.
Bye-bye. Take care.
Have a great day.